Hi, my name is Tanya Singh, and this is my lab report. This lab investigates the motion of a spring mass system using both experimental data from tracker and a computational model. The goal is to compare predicted motion with observed motion and evaluate whether the model accurately represents the system. Overall, the model captures oscillatory behavior and conserves energy, but there are noticeable differences between prediction and experiment. The system consists of a mass attached to a spring moving in two dimensions. The surroundings include the Earth, which provides gravitational force, and spring, which exerts an elastic restoring force. These are the only forces considered in the model. The coordinate system is defined with the origin at the attachment point and the y-axis aligned with the spring. Experimental data was obtained using tracker by analyzing a video of the oscillating mass. The motion was tracked frame by frame starting at release. A known length was used to calibrate the scale, and time between frames provided timing information. The X and Y position data were exported into a CSV file to be used in the computational model. The computational model reads the experimental data from the CSV file and simulates motion using Newton's second law. At each time step, the forces are calculated, the net force is determined, and the velocity and position are updated. The model outputs predicted motion and compares it directly to the experimental data along with plotting energy changes. The motion is governed by Newton's second law, where the net force determines acceleration. Gravity acts downward with constant magnitude, while the spring force depends on how much the spring is stretched and acts in the opposite direction. The system's energy consists of kinetic energy, gravitational potential energy, and spring potential energy, which are used to analyze energy conservation. The model uses measured values for the mass, spring constant, and relaxed length. The initial position is taken directly from the tracker data, and the mass is released from rest, so the initial velocity is zero. The model assumes an ideal spring and neglects any air resistance and energy loss. When comparing motion, both the model and experimental data show periodic oscillations, meaning the model captures the general behavior of the system. However, there are differences. The experimental motion has larger amplitude in the x direction, while the model shows larger oscillations in the y direction. These differences indicate that the model is qualitatively correct, but not perfectly accurate. Energy plots show that kinetic, gravitational, and spring potential energy all oscillate over time, meaning energy is constantly being transferred between forms. The total energy change remains very close to zero, indicating that energy is conserved. Therefore, the energy principle is satisfied in this model. The oscillation period was estimated from the tracker data by measuring the time between repeating peaks in the x position and y position graphs. From the x position data, the period is approximately 1.65 seconds, and from the y position data, it is approximately 1.55 seconds. These values are very close, differing by about 0.10 seconds, which indicates consistent oscillatory motion. The small difference is likely due to measurement uncertainty in tracker and the fact that the motion is primarily vertical, making the y position estimates slightly more reliable. Sources of error include inaccuracies in tracker measurements, such as marking the mass position and setting the scale. The model also assumes an ideal spring and ignores air resistance and damping, which are present in real systems. These factors contribute to the differences between predicted and observed motion. In conclusion, the computational model successfully reproduces oscillatory motion and satisfies the energy principle. However, differences between the model and experimental data highlight the limitations of the model and measurement process. Overall, the results support the validity of the physics principles used.